Assalamu alaikum. Welcome to this Matlab tutorial. In this tutorial I am going to teach you how to design load frequency control of thermal or hydro power plant using transfer functions in Matlab Simulink Software. I have taken an example from the book Power System Analysis by Hadi Sadat, Chapter 12, Example 12.1. Consider the example which consists of an isolated power station having following parameters. As we are going to design the model using transfer functions, therefore we need the time constants of various equipment used in the power plant, such as governor, turbine, generator. The power plant has rated power of 250 megawatt. And all of a sudden a load of 50 megawatt is increased. Due to this, system frequency will vary. We have to build Simulink model of the power system and measure this frequency deviation in per unit. It may be noted that I have written the word thermal and hydro, whereas in the question it is not mentioned. It is because the transfer functions can be used for both power plants. The only difference between these two power plants lies in the values of their time constant. Therefore, if you have the time constant values, then you can model any power plant. The mathematical solution as well as model of this example can be found in the Hadi Sadat book. I am going to model it again in order to explain various other results which can be obtained from this model. For your convenience, I have uploaded the PDF link in the description section. You can download it from there. Let's start. Just click on the Simulink icon to open it. Click on this icon to open a new model. First we need to save it. You may save it with any name of your choice and in any folder. To design the model of power system using transfer function, just look at the block diagram of the power plant based on transfer functions. It may be noticed that the model consists of transfer functions of governor, turbine, generator named as rotating mass and load. In the feedback, speed regulation is placed. It means that to model the power plant we need transfer function block, gain block, sum block and input signal block. To get the transfer function block, go to Simulink library and go to continuous. You can see here transfer function block is available. Take this block and bring it in the model. The time constant for governor is 0.2 as given in the example data. Therefore, double click on the transfer function block and write here 0.2 and press OK. Write here governor to represent the transfer function of governor. Now we need turbine transfer function. To do this, copy this transfer function block and paste it here. The time constant of turbine is 0.5 as given in the example data. Therefore, double click on the transfer function block and write here 0.5 and press OK. Write here turbine to represent the transfer function of turbine. Now connect both blocks with each other. Look at the figure again. Now we need summer block. Take the add block from here and bring it in the model. Double click on it, a window will open. Put one negative and one positive symbol as shown in the figure. Now we need the input signal which consists of change in load demand. For this purpose we need step input signal. To get this, go to source and take the step input signal from here and bring it in the model. Connect it with the sum block. Double click on it, a window will open. Write step time to 100 Just look at the example data which shows that for a 50 megawatt change in load, delta PL is 0.2 in per unit. Therefore, put here 0.2 as the initial value as well as final value and press OK. Look at the figure again. Now we have to connect the rotating mass and load transfer function block. It may be noted that inertia constant h is multiplied by 2. The inertia constant is given as 5 seconds. It will be multiplied by 2 becomes 10. And d is equal to 0.8 as given in the example data. Now copy the transfer function block and paste it here. Connect it with the sum block. Double click on it. Write here 10 and 0.8 and press OK. Write here inertia and load. Look at the figure again. Now we have to put speed regulation value. For this purpose we need gain block. Take the gain block from here and bring it in the model. Connect this gain block with inertia and load block. Write here 1 upon R to represent the speed regulation. The speed regulation given in the example is 0.05 per unit. Therefore, 1 upon R will become 20. Double click on the gain block and put here 20 and press OK. Look at the figure again. Now we need to add some block to complete the feedback loop. Copy the sum block and connect it here. Double click on it and use one negative sign only and press OK. Connect the gain block with the sum block to complete the loop. Now we need scope to see the frequency deviation graph. Take the scope from here and bring it in the model. Connect the scope here. Write here frequency deviation in per unit. Now you can run the simulation. Before running the simulation we need the power GUI block. To get this block just write it in the search term of Simulink library and enter. It will show the power GUI block. Copy this block and paste it in the model. Set the simulation time to 20 seconds. Now you can run the simulation. Double click on the scope to see the frequency deviation response in per unit. Compare the results with the result in the example. You can see both results are correct. Now to get further clear idea, we want to change this frequency deviation in Hertz. We know that change in frequency actual is equal to change in frequency per unit into frequency base. The base frequency is 60 Hz. Therefore, multiply the result with the gain in order to get the frequency deviation in Hertz. To do this, copy the gain block and connect it here. Double click on it. Put here 60 and press OK. Write here base frequency. Now connect the scope to measure the frequency deviation in Hertz. Write here frequency deviation in Hertz. Now you can run the simulation. Double click on this scope to see the frequency deviation in Hertz. Compare the answer with the answer obtained in the example. You can see both answers are correct. This is the frequency change when a load of 50 megawatt is suddenly added to the power plant. Now, what will be the original frequency of the power plant? The original frequency in Hertz is given by F actual is equal to F original plus change in frequency. To do this, we need again sum block. Copy this sum block and paste it here. Double click on it. Change the signs to both positive. Connect one signal here. To add 60 Hz frequency, we need constant block. Take this block from here and connect it here. Double click on it, write here 60 and press OK. Copy the scope and connect it here. Write here actual frequency in Hertz. Now you can run the simulation again. Double click on the scope. It shows the power plant original frequency when 50 megawatt of load is added. When the load is increased, the system frequency is decreased. Therefore, in this case, frequency decreases to 59.424 Hz. You can zoom it to see the actual value. Now we want to see the power graphs. First, you may notice that per unit change in load is 0.2. Therefore, to do this, just copy the scope and connect it here. Write here change in load power in per unit. Now run the simulation. Double click on the scope in order to see the change in load power in per unit. You can see here the value is little bit lower than 0.2 per unit. It is because due to load change, system frequency has gone to 59.424 Hz. The frequency has not recovered to 50 Hz. When the frequency will recover to 50 Hz, then this will show exactly 0.2. I will show it later in this tutorial. Now we need to convert this change in load power in per unit to megawatt. We know that the actual change in load power is equal to per unit change multiplied with base load power. The base load power is 250 megawatt. To do this, copy the gain block and paste it here. Double click on it and write here 250. Connect it here. Copy the scope and paste it here. Write here the base MVA. And write here change in load power in megawatt. Now run the simulation. Double click on the scope to see the change in load power in megawatt. You can see the change in load power is not exactly 50 megawatt, it is little bit lower than it. Now we want to see the total load demand after the sudden load change. The total load power will be equal to rated load power plus the change in load. To do this, copy the sum block and connect it here. Copy the constant block and connect it here. Double click on it and write here 250. Connect the other sum port here. Copy the scope and connect it here. Write here load power in megawatt. Now you can run the simulation again. Double click on the scope to see the total load power. It may be noticed that total load power is not equal to 300 megawatt. This is due to the reason that frequency is not recovered to 60 Hz. If frequency is recovered to 60 Hz, the all power magnitudes will be correct. To restore the frequency to 60 Hz, we need some controller. Commonly, we need PID controller to restore the frequency. Therefore, take the PID controller block from here and bring it in the model. Connect this PID controller in the feedback loop. PID controller needs the values for its proportional, integral and derivative gain. PID controller needs proper tuning in order to get the desired response. For this purpose, we have to change the parameters again and again in order to get the desired response. Initially, we choose random values of p is equal to 5, I is equal to 3 and d is equal to 1. Now run the simulation and see whether frequency is restored to 60 Hz or not. You can see frequency now goes closer to 60 Hz but still not reached to 60 Hz. It means that we have to change the PID controller parameters again. Now change the P is equal to 10, I is equal to 5 and D is equal to 2 to see the effect. Now run the simulation and check the frequency. You can see frequency is going closer to 60 Hz but still not reached to 60 Hz. It means that we have to change the PID controller parameters again. It is a continuous process. However, to save the time, I have already tried many values and now I am going to put the P is equal to 50, I is equal to 30 and D is equal to 10 in order to get the desired response. Now run the simulation and check the frequency. You can see frequency has now reached to 60 Hz. It means that now at this moment, change in frequency in per unit and Hertz is reduced to 0 as shown here. Now I am going to show you change in load power in per unit. You can see now it is exactly 0.2 per unit. You can also check the change in power in megawatt graph. It is 50 megawatt. Finally, see the graph of total load demand which is equal to 300 megawatt. Hence, it is proved that when frequency is restored to its original value, the results of the load powers are also correct. At this stage, I want to highlight that don't underestimate this model. One may think that this model simply consists of transfer functions only, how it can provide the full information of power system, its frequency behavior and change in power magnitudes. To prove this, I have designed this model and have proved how this simple model provides all the details of frequency, power magnitudes accurately. This topic is commonly known as load frequency control. It is because in this model we have controlled the frequency and load power. Similarly, with little modification, this model can be converted into automatic generation control model to provide the sharing of power between the two generating plants. Now I am going to highlight the research trends in this topic so that if anyone is interested, he or she can do his bachelor project. This topic can also be used in the fulfillment of 1 or 2 objectives in the master and PhD degrees with modifications. As I have already discussed that response of the PID controller is to be tuned by using hit and trial error method. The frequency response of the power system greatly depends upon the performance of PID controller tuning. Therefore, we can use various methods to tune the PID controller or replace the PID controller with latest intelligent controllers. Based upon this, one may choose the following topics for their research. Load frequency control of thermal hydro power plant using PID controller tuning with board plot, or just replace with using fuzzy logic controller, or using artificial neural network, using radial basis function neural network, using probabilistic neural network, using adaptive neurofuzzy inference system, using support vector machine. These are the few topics about load frequency control. Now if we modify this load frequency control to automatic generation control, then all the above topics can also be chosen for the bachelor, master or PhD research. To save the time, I just show you the title here. I have only replaced the load frequency control with automatic generation control. Friends, these are the few research topics that can be chosen by anyone to perform his or her research. That's all for today's tutorial. I hope you really enjoyed this tutorial. Friends, I upload many videos based on various topics of power system and motivation on regular basis. Therefore, don't forget to subscribe my channel in order not to miss my latest videos. And don't forget to share my videos with your friends and class fellows so that they can also get benefit from these videos. Thank you very much.